Welcome, students. I know it's been a while since I've made a video, but I know you're happy that you get to watch another video in class, awkwardly, while I'm in the classroom right here. See? Everyone look at me. There I am. Hi. Okay, awkward moment, but I'm full of awkward moments. I think you're going to remember one thing from high school. It was perfectly not awkward until I took Mr. Bestling's class. Oh boy. All right, speaking of awkward, let's get this going. We are doing today's lesson. I'm skipping 8.3 for now. We'll get back to it next lesson. But we're going to look at section 8.4, which is really our last major two-sample test. And this is going to be the two-sample z-test for p1 minus p2. That is a difference of proportions. So what are we going to be doing? That's a fantastic question. I'm glad you asked that. All right, you asked that, didn't you? All right, so in this section, 8.4, we will be testing whether there's a significant difference between two proportions, essentially from two populations. Because these are binomial events, that is, if we're taking sampling from a population, looking at a proportion, that is, maybe, I don't know, we're sampling 100 people and trying to find out how many eat mayonnaise with their French fries. We consider this a binomial event, and we learn that if we have a large enough sample size or trial size, that these binomial events follow a normal distribution. So we're going to be essentially going back to our z-tables and using a z-distribution. Wait, was there more? Okay, I guess not. All right, we're going into the pooled proportion first. So for our t-tests, we said no pool party, no pooling for t-tests. And the reason why we didn't really pool for t-tests was because to pool, we're assuming that the two variables not only have equal means, but also equal variances, that is, or standard deviation. Well, it just so happens if I am testing a proportion, my null hypothesis will assume that the proportions are equal. And if two proportions are actually an equal proportion, there it goes. If two variables are in equal proportion, then their variability only depends on the sample size. Okay, what is he talking about? Well, let's just put it this way. There's no standard deviation with just a categorical variable by itself. But if I do something like, I'm going to go over to the next slide. Oops, I'll go back to that. But if I do something like, say, flip a coin, and a coin should have 50% heads, so the probability of success is 0.5. And let's say I flip it 100 times. We had learned in a previous chapter, chapter 5, that how many heads would I expect? Well, that's going to be NP, and that is my trial size 100 times P, the probability of success, or 50. Right? Because I expect 50% heads, 50% of my sample of 100. But we learned that the standard deviation of x, or what did we have? We had that symbol for it, I believe, was the square root of npq, which is 1 minus p. So when we look at that, square root of npq, and this is for the number of heads, not the proportion of heads, whatever that is, I think if my memory serves me correctly, it's about 5. Well, what does that mean again? In this case, NP is 50, which is greater than 5, and NQ is also 50, which is greater than 5. What we had learned in Chapter 5 is we have a large enough sample size that the distribution of heads should look approximately normal, with a mean of 50 and a standard deviation of, okay, I made up this number a little bit, I think the actual number is 4.7, but it's the square root of NP, you can double check this if you really want to, but you don't have to, of 5 times 0.5, so it's that standard deviation. In other words, if I'm flipping a coin 100 times, on average, I'd expect to get 50 heads with a standard deviation of 5. So using our normal probability, about 68% of the time, I should be getting between 45 and 55 heads. And 95% of the time, I should be getting between 60 and 40 heads. And if I'm getting over 60 heads or under 40 tails, you can tell that's going to be a fairly unusual event. Why am I talking about all this? Would you like to answer that, Black Cat? No, not now. You're just going to meow at random times. All right, fine. Okay, I don't even know why I got into that. All right, neither does my cat. So, definition, we're going to call this a pooled proportion. It's going to be a big pool party. And what we're going to be doing is the pooled proportion is going to be the combined proportions of successes to trial size in both populations. So go ahead and write that down. I'm going to switch slides in just a minute and give you a formula for the pooled proportion. And if you see here, we're going to be calling it, your book calls the pooled proportion P bar. So it's like the average proportion. Doesn't sound too bad, right? Sounds awful? Well, too bad, man. It's too late to drop the class now. You're stuck with me for the rest of the year. We're almost there anyway. Woo! Alright, so the pooled proportion. And then we'll go to the rest of the what we need to know about the test. But this is going to come up here. Pooled proportion. And the formula for the pooled proportion is P bar is going to equal x1 plus x2 over n1 plus n2. So the idea is from population, and in fact, let's just go ahead and define these now. P hat 1 is going to be my proportion of successes to the total sample size from population 1. And P hat 2 is going to be my proportion from the second population, that is x2 over n2. And again, I'll try to wrap this all up with a smashingly realistic example at the end of the lesson, because that's how I roll. Okay, so let's just get into what we need to know for the two sample z test for P1 minus P2. You ready to switch slides? No, not yet. Got it? Hurry up. 3, 2, 1. All right, so the hypotheses for a two sample z test for P1 minus P2. Again, this is going to depend if we're right-tailed, left-tailed, or two-tailed. So let's start with the right-tailed. Sorry for my awful handwriting. For a right-tailed test, we have, I'm just going to start with the alternative because to me it's easier, that P1 is going to be greater than P2. So the null is going to be that P1 is less than or equal to P2. And this is a right-tailed test. For a left-tailed test, just the opposite of a right-tailed test, we're going to get that the null is P1 is greater than or equal to P2, and the alternative that P1 is less than P2. And lastly, for our two-tailed, for our two-tailed, we have the null that P1 equals P2. That's a P, believe it or not, that first one. That doesn't look like a P. That was a P. There it goes. P1 is not equal to P2 versus P1 is not equal to P2. So here's our left-tailed test. We're gonna be rejecting samples that are too low, where the difference is too low. And in two-tailed, it can be either too big or too small. All right, so what are the conditions? Well, again, we're going to need random samples. So this is going to require 2 independent random samples. And again, by independent random, by independent we mean that the 2 samples should not be matched in any meaningful way. One shouldn't influence the other. And normal, do you remember what the normal condition is for a one sample z test for P1 for P? No, you forgot. I know, because I've been grading your tests. That was a bad joke. Well, we need that NP is greater than 5 and Q is greater than 5. And that was Q hat. But now it's going to be, we got to check it for both populations. So our NPs and NQs should all be greater than 5. So that applies for the first population, and it applies for the second population. Now remember that whole continuity correction that we did in chapter 5? What, you forgot it? Well, I got good news for you. You can go ahead and forget about it, because we won't use it. But just to let you know, there is computer software that uses the continuity correction. I know my favorite software, R. If you do a z-test for P1 minus P2, we'll use the continuity correction unless you turn it off. Your calculators, which I'm assuming you're going to be using for the most part, do not use the continuity correction, whatever that was anyway, right? Right. All right. Let's get into our test statistics. So our test statistics. And again, yes, our calculators can do this all for us, so we'll get there later. You could figure out how to use it yourself. All right, so we're going to have, again, P1 hat. That's the proportion from population 1. That's X1 over N1. P hat 2, that's going to be X2 over N2, the number of successes. We set our pooled proportion, pool party. We just add the two, add the combined total number of successes over the combined sample size. And this is going to be P bar, or the pooled proportion. Now our Z test statistic is going to be P1 hat minus P2 hat all over. Now you're wondering, where does this pooled proportion come into play? Well, it comes into play in the standard error, which is the denominator down here. So we're going to need P bar and Q bar, and that's a good point. Let's go write this down there. Q bar is just going to be 1 minus P bar. Again, that's the P bar is the combined probability of successes. Q bar is the combined probability of failures. And then this is all going to be over 1 over N1 plus 1 over N2. And it's the square root of all that, right? Ooh, looks like a crazy formula, but I've seen worse. I can make it harder if this is if you want. I can make it easier too. No, I can't. I can't make it any easier. Just kidding. We just got to do what we do. And then, like before, I'm not even going to write it down because we know now how to make. We're going to use this z-score as just a simple z-score. Doubling the value under the doubling the value if it's a two-sided test. So then we're going to find p-values like we've done and make decisions and conclusions like we have already been doing all semester long. Make decisions and conclusions. So let's put it all together. Sound like a plan? Make a good example out of this. Do men and women like mayonnaise with their fries in different proportions? I'd hope not. We randomly sampled 312 men and find that 243 like mayo with their fries. We also randomly sample 208 females and find that 119 like mayo with their fries. We'll use a 5% significance level, alpha equals 0.05. So we'll write the null and alternative hypotheses. We'll define the parameter. We'll check the necessary conditions, calculate the test statistics, and finally make our conclusion. So you guys ready? You excited to tackle this problem? You excited to finally answer the question, do men and women like mayonnaise with their fries in different proportions? You're not that excited? Fine, okay, fine. I made these numbers up, but you can do it yourself. Okay, you can change your stats project and sample 1,000 men and 1,000 women and tell me. All right. Okay, so let's start with the null and alternative hypotheses. So the null hypotheses. So again, looking back at the question is, Kitty, stop making all that noise. Thank you. The question says, do men and women like mayo with their fries in different proportions? So ask yourself, should that be right, left, or two-tailed? Two-tailed. Somebody said two-tailed. Nobody said two-tailed. No, just kidding. Somebody said it. Somebody in the back row. Okay, they were in the middle of the classroom, but still. All right, so we have the null p1 equals p2 versus p1 does not equal p2. And again, it helps to define your parameter. It not only helps, I didn't mention which one is population 1 and which one's population 2, so I need to do that. So where p1 and p2, that was an and, are the true proportions of men and women I'll put in my respectively right here. Respectively, who like mayo with their fries. Mayo with their yummy, yummy French fries. Okay, let's check the conditions, part B. So, random? Well, it did state that both samples were randomly selected. And they're independent samples. Both samples were randomly selected. And what is the normal condition? It's not the sample size is over 30. Sample size over 30, and again, a lot of people made this mistake on their tests. It's understandable. I don't blame you. I still love you. It's okay. But we need to really get this sample size over 30 different. We need to distinguish the difference between the sample size being over 30, and in this case, this is going to be our NP, NQs greater than 5. Sample size over 30 works for tests for means. And again, that is if the variable I am looking at is a numerical variable. Like if I took the heights, if I took 50 people's heights, or if I took 50 people's GPA. What's different here? This is proportions. If I'm asking one person, I'm not writing a number like their GPA. Your GPA is 3.8. No, I'm writing down either a yes or no. You know, a French fries, your mayo with your French fries, yes or no? Yes. You? No. So the sample size being over 30 doesn't work for this. That's the central limit theorem. this is what I'm doing is I'm doing my NP and p1 hat greater than 5. And what this is this is my normal approximation to a binomial curve. It is, let me just go back here. It is when I did this example up here. It's saying my sample sizes are large enough so that the distribution of my successes and failures is approximately normal. Remember when we did that? It was like if I only flipped a coin 3 times, and if I looked at the number of heads, okay, I'd get 1, I'd get 2, and sometimes I'd get all 3, and sometimes I'd get no heads. This is mound-shaped, it's nice, but it's not perfectly normal because I only have essentially 4 things that could happen. I could get 0, 1, 2, or 3 heads. But in this case, I flipped enough coins that I can get 50, 51, 52, 53, 54, 55 heads, etc., etc. So I have a lot more options available, if you will, a lot more possible outcomes, and that the distributions of this is going to follow a smashingly beautiful bell curve with this mean and this standard deviation. That's this mean and this standard deviation. So sorry I got sidetracked there, but I just really wanted to make sure that we know the difference here between when do we check that it's just simply over 30 and when do we do the NP and Q's greater than 5. And you'll actually see something nice here. I'm going to check all these in just a second, but something nice is going to happen that we did see before. A little shortcut on this. And to Q2 hat has to be greater than 5 too. So in this case, all the NPs, all the NQs have to be greater than 5. Okay, so looking at the male population here of the yummy French fry lovers, the sample size was 312. Sorry, I forgot my numbers here. And 243 out of those 312 like mayonnaise. Well, check it. What happened to my denominator there, the 243 over 312? Psh, psh. Canceled out, right? What am I left with? Not a 3. I'm left with 243. What was that number, 243? Yeah, that was my number of successes. That was the number of people, there it is, psh, who liked mayonnaise with their French fries. So I can actually do this for all of them. Isn't that nice? So with the females, we had 119. And last time I checked, 119 is greater than 5. And likewise, if 243 was the number of successes, I can do the same thing with the number of failures. So if 243 people liked mayo with their fries, how many were left over who didn't like mayo with their fries? Oh man, my head hurts. I gotta do this. 312 minus 243, 79, or was it 69? Sorry, 69. 69 is greater than 5. Check. And in this case, 119 out of the sample size of females was 208. So if my math serves me correctly today, that's going to be 89 females who did not like mayonnaise with their French fries. And last time I checked, 89 is indeed greater than 5. We're almost there, folks. We're almost there. So let's calculate our test statistics. So I have a few different test statistics I need to calculate. Number 1 is going to be p1 hat. And p1 hat, again, in this case, is going to be the proportion of, gosh, my stylus even kind of ripped too, so it's bad enough that my handwriting's not the neatest in the world, although I will say it's not the worst in the world either. But it's just really hard to write on an iPad because I can't actually rest my hand on the actual iPad or all sorts of funky things happen. Alright, so my P1 hat was my 243 over my 312 males who liked mayonnaise with their French fries, which it helps to get a decimal for. So I will do that right now, which was 0.7788 or 77.88% of the population. I think it's a little short. I believe that number is an underestimate. In Holland, it would be an underestimate. Where I'm from, in Holland, that would be an underestimate. Here in America, no, that's probably an overestimate. Regardless. Okay, P2 is going to be my 119 females out of my 208 total who liked who liked mayonnaise with their French fries, and that's going to be 0.5712. What are you doing, weirdo? What are you doing? So if you look already, ask yourself, do you think there's a big enough difference here? There's 77, nearly 78% of the males of my sample ate French fries versus 57% of the females. It seems like a pretty big difference. But what do we do in a hypothesis test? Clearly there's a difference between my sample. But the idea is, could this difference have occurred by random chance if the two proportions were actually equal? How likely is this to occur by random chance? Or could it just be that they're not the same? That, looks like in this case that the males seem to prefer mayonnaise with their fries a little bit more than females. Okay, let's calculate the pooled statistics. So this is going to be total. Everyone in my sample, no matter the gender, how many of them preferred mayonnaise with their French fries. So that's going to be 243 plus 119 out of 312 plus 208. 243 plus 119, that's a 9, believe it or not. That's 362 over 312 plus 208 is 520. So total in my sample, I got a total of 69.6. That's 6162% after rounding it appropriately. So let's calculate my test statistic. This is going to be my Z. So it's going to be P1 hat minus P2 hat over P bar, Q bar, and then it's going to be 1 over N1 plus 1 over N2. And let's just go ahead here and find Q bar again is going to be 1 minus this. So that's going to be 0.3038. Alright, so this whole thing should be 0.7788, my P1 hat minus P2 hat, over the square root of 0.6962, that's P bar, times Q bar, oops, that's a 3, excuse me. And then that's going to be over 1 over my first sample size, 312, I'm running out of room, plus 1 over my last sample size, which was 208. And I'll close it. I'm going to pause my video and calculate this. And I got a Z-score of a quite surprisingly large 5.02. Alright, lastly, what's your p-value? What's your p-value? What's your p-value? Well, if you are using the normal table, this is 5 standard deviations above the mean, far greater than the table provides. The table only provides standard deviations up to 3 standard deviations up less than or greater than the mean. So if you're using the z table, you can say that the p-value is almost 0, even though yes, we do have to double it. But I have some technology in front of me, and that is R, my R calculator, and I got, using R, the area to the right of 5.02 standard deviations. There's 0. There's going to be my left tail. Since this is a two-tailed test, that means I'm going to have to double this p-value. But I got this number as e to the -7, so that's going to be at decimal places, and 6 zeros followed by 2 6. So my total p-value, since this is a two-sided test, but you can see that it almost doesn't matter because this is going to be like almost 0, is going to be 2 times 0.0000. Did I write enough zeros here? Something weird happened to my computer here. So that's going to be, let's see, a 0.0000000. Nope, not a 0.52. Yeah, so what does that mean? Interpret that p-value. Well, if men and women like mayonnaise in equal proportion, the probability of me getting a difference as big as I observed in my sample, or bigger, is that tiny, tiny number. Extremely rare, extremely unlikely. So unlikely that my first part of the statement, the if part, was probably wrong. That's my assumption that the two proportions are equal. So, lastly, I could safely conclude, since my p-value is so small, since my p-value is less than alpha, we reject the null hypothesis. There is convincing evidence. Sorry, my stylus is dead. I've just torn this thing to shreds. There is convincing evidence that men and women like mayo with their fries. And you would never, do what I just did if this was actual academic writing, right? In different proportions. Okay, any questions? Yeah, you in the back? 12. Good question. Anyone else have any questions? Okay, you by the window. Can you speak a little louder? I can't hear you. Oh, that's a great question. The answer to your question is 93. Okay, students, I hope you enjoyed this video, and have a great day.